In 1895, Harvard University had a problem. The Frogg lecture room, part of the recently completed Frogg Art Museum, was rapidly developing a reputation for the terrible quality of its acoustics. Speech intelligibility in the space was so poor that it was largely abandoned as unusable, and high-profile critics were applying mounting pressure on the university leadership to rectify this embarrassing situation. The challenge of improving the lecture room's acoustics had already been passed back and forth between several senior staff at Harvard's physics department, until eventually it was handed to a young professor of little previous note by the name of Wallace, Clement, Sabine. The story of the Frogg lecture room up to this point was hardly unique. A review of lecture rooms, theatres and concert halls constructed the world over up until the turn of the 20th century reveals a pretty hit-and-miss picture. Indeed, some of the world's most famous concert halls are notorious for their challenging acoustics and long histories of acoustic revisions. But Sabine's work elevated the Frogg building to a very special place in the history of the field of acoustics. Over the course of several years, Sabine and his assistants spent night after night experimenting by bringing different materials and furnishings into the lecture hall in order to quantify their acoustic effect. The result of Sabine's efforts was the foundation of the modern field of architectural or room acoustics. Hello Church Sound Summit, it's great to be here talking to you all today. My name is Patrick Smith and I'm a Principal Engineer at Sandy Brown Associates. Sandy Brown is the UK's largest independent acoustic consultancy with a history going back over 50 years. Since 1969, we have been at the forefront of building acoustics and are recognised experts in the acoustic design of studios, auditoria and performance spaces. Personally, my particular area of interest lies in the audience or congregational experience of sound in event spaces, and my role exists at the nexus between building acoustics and sound system design. I previously have over a decade's experience working in live audio, initially as a freelance sound engineer and later as an installations project manager at SFL Group, a leading UK audiovisual integrator, where, among many other projects, I led the installation of the new D&B Audio-Technica loudspeaker system at the Royal Albert Hall in 2018. Over my career so far, I have come to believe passionately in the value of an integrated approach to acoustics and sound system design. And as a Christian, I'm particularly passionate about the application of their approach in the church. Outside of the current pandemic, churches are consistently among the busiest, most populous live event spaces around the world. The ability to communicate clearly and to facilitate engaging, life-changing worship experiences is at the heart of everything we do when we gather together as a community in our church buildings. And the quality of sound, and by extension the quality of acoustics, is central to those aspirations. Sabine's work at Harvard was just the start of a field of acoustics that continues to develop and expand to this day. And I'd like to spend just a few minutes now introducing you to some of the concepts and principles of this field, hopefully so that we can all begin to understand how they might be applied in our church contexts. When we create sound in an enclosed space, our listeners hear two things. First, they hear the direct sound, which has followed the shortest path in a straight line from the sound source, and as sound travels at a fixed speed of approximately 340 meters per second, the direct sound is always the first instance of a sound to arrive at the listener. Secondly, they hear the reverberant or reflected sound, hundreds or even thousands of copies of the original direct sound, which have followed various paths around the room before arriving at the listener. Depending on the length of the path taken and the properties of the materials encountered, these copies of the sound will reach the listener at varying times and with varying degrees of intensity. However, generally what we expect to see is a fairly consistent rate of decay over time. Sabine first formalised the definition of this effect with the introduction of the concept of reverberation time. Although many other measures have since been developed to quantify room acoustics, reverberation time remains probably the most fundamental measure of the acoustic performance of an enclosed space. Put simply, reverberation time is the length of time it takes for a sound to drop from its initial level by 60 decibels. 60 decibels is about the level of typical conversational speech, so this is a particularly good indication of how long the sound from speech will linger in a space before it decays below human hearing. By evaluating the range of different performance spaces, Sabine determined that a reverberation time of around 2 to 2.25 seconds was optimal for a classical concert hall, whereas a time of under 1 second was preferable for a lecture hall or other space intended primarily for spoken word. Not only did Sabine give us a definition of reverberation time, but from his experimental data, he also derived the basic formula that allows us to manipulate it. By testing in the Frogg lecture hall, as well as several other spaces, Sabine discovered that reverberation time was principally a product of just two factors. Firstly, the volume of the space, and secondly, the total quantity of acoustic absorption in the space. In terms of volume, Sabine's equation tells us quite simply that, all other factors being equal, larger spaces will tend towards longer reverberation times and smaller spaces to shorter reverberation times. In terms of absorption, he found that different materials and furnishings were relatively more or less absorptive than others, and that this could be quantified in terms of an absorption coefficient for any specific material. Absorption in a space could therefore be managed either by using more absorbent materials, i.e. with higher absorption coefficients, or simply by increasing the quantity of existing absorbent materials. Technically speaking, the absorption coefficient of any given material varies with frequency. The consequence of this is that reverberation time also varies with frequency. Though in most cases it's sufficient to typify the reverberation time based upon the mid-frequency performance, known as TMF. Similarly, we often simplify the quantification of acoustic absorption either by using a single weighted coefficient to typify the full frequency range, or by using an alphabetical classification system, both of which are defined by international acoustic standards. There are three basic types of acoustic absorber. The most common are porous absorbers, made of mineral fibre or foam. They are cheap, lightweight, and they can be covered in fabric to provide a range of finishes. Porous absorbers generally aren't great at low frequencies, but ramp up in performance through the mid-frequency and are very effective at high frequencies. Increasing the depth of the material will shift the performance down towards lower frequencies and also increase the overall absorptive effectiveness. So, for example, a 25mm deep absorber can typically only achieve Class C absorption, whereas a 40mm deep absorber of the same material could often achieve Class A. There are, of course, practical limitations on how deep a panel can be or how deep a panel can be accommodated within a certain space. So generally, porous absorbers are only affected down to frequencies of around 200 to 300 Hz. The second type of absorber is a membrane or panel absorber. These feature a large panel or membrane which is tuned to resonate around a particular frequency, thus absorbing the energy which is then dissipated via a damping material. Panel absorbers feature a pronounced peak in performance at the resonant frequency of the panel, which is dependent on the panel dimensions, but it's typically designed to be at a relatively low frequency. The panel will provide some absorption at frequencies above and below its tuned peak, but the roll-off is quite rapid, so panel absorbers are mainly used to control discrete low-frequency issues. The final type of absorber is a cavity absorber. The most common type is known as a Helmholtz resonator. In this case, we have a carefully tuned perforated finish which allows sound energy within a limited frequency range to enter a resonant cavity behind the absorbent panel where it's subsequently dissipated. Cavity absorbers are effective over a very limited frequency range, even more limited than panel absorbers, but they typically require less depth and can be concealed within various hard finishes such as wood or metal panels, which lends them some aesthetic advantages. It's worth noting, of course, that many building elements which are not designed specifically for their acoustic properties may nonetheless provide one or more of these classes of absorption. Most commonly, soft furnishings, carpets, curtains, etc. provide a ready supply of porous absorption to venues, at least partially mitigating the requirement for specific acoustic treatment in many instances. On the other hand, modern design trends towards harder finishes and a cleaner aesthetic are leading to spaces which are naturally more reverberant and increasing the need for detailed acoustic design and dedicated finishes to compensate for that general lack of inherent absorption. These basic concepts of reverberation time and absorption have been refined over the years, but haven't really changed fundamentally over much of the last century. We still apply Sabine's formula and some derivatives of it as basic predictive tools in room acoustics today. There are, of course, limitations in these basic principles. One of the biggest being that Sabine's formula is only strictly accurate in very diffuse spaces, by which we mean reverberant spaces in which reverberant energy is distributed evenly throughout the space. In practice, this is rarely the case. Strong reflections from specific surfaces, focused reflections as a product of venue geometry, echoes, flutters and standing waves are all acoustic phenomena that result in uneven, localized variations in the reverberant field, which can impact the listener experience. Generally, a more diffuse space is preferable for nearly any application. This is an area where historical Anglican church buildings often have something of an advantage. Their inherent geometrical complexity, combined with intricate architectural detailing, provides a naturally diffuse environment that is often lacking in more modern buildings. By the era of the Frogg lecture hall, there was a particular trend for circular or semicircular buildings and domed ceilings, which are now understood to be uniquely acoustically problematic due to the way they act to focus reflections at specific points in the room. Similar features are found in many worship spaces of that era, and in the UK particularly, we find a lot of Baptist and Methodist buildings date to this period. Modern church buildings have a tendency to be more boxy in shape. For instance, many churches in the UK meet in converted warehouse units or rented halls, which are inherently very rectangular and therefore not particularly diffuse. There's also quite a tradition in the UK of converting Art Deco venues into churches. Many of these were once cinemas or theatres, which have subsequently found other uses, most prolifically as bingo halls, before falling into further disuse and eventually being taken on by churches. And particularly in many towns and cities across the UK, these venues are favoured by Pentecostal congregations. They're used a lot by Pentecostal groups. These again tend to be very boxy spaces in terms of their overall geometry, though they do often benefit from more intricate decorative detailing. There's no singular definition of the diffusivity of a space, and accordingly there's no simple acoustic measure that can be used to quantify this characteristic, though deductions can be made from the shape of the reverberant decay. In a highly diffuse space, reverberation decays evenly, whereas in a non-diffuse space, there's often a noticeable discrepancy between the early decay time, that is, a measure of the reverberation time extrapolated from only the first 10 decibels of decay, and longer measures such as T20, T30 and T60, which evaluate the first 20, 30 and 60 decibels of decay respectively. When we put a sound system in an acoustic space, it's important to recognise that audio quality for the listener becomes contingent upon a much wider range of factors. Obviously, in the case of musical sources, the quality of the art form is important. Similarly, the articulation of the voice for speech sources. If the input isn't of a good quality, there's very little we can do in terms of either physical acoustics or sound system design to rectify these insufficiencies. There's also the quality of the equipment and, of course, the skill of the engineer behind the mixing desk. These areas will be the focus of other talks throughout the summit. But if we assume that we have a decent band, we have reasonable quality input and control equipment, and we have a capable engineer behind the sound desk, we discover that actually it's the acoustic of the building and the loudspeaker system together and the interaction between the two which have the greatest bearing on the overall quality of the listener experience. There's several acoustic measures that have been developed to try and objectively quantify that experience. Probably the most widely used is the speech transmission index, which is a scale from 0 to 1, which quantifies the quality of speech transmission from a sound source such as a loudspeaker system to a defined listener position. Speech transmission index and the methods of its measurement are defined in international standards, and for certain types of sound systems, so for example voice alarm, where sound systems are used as part of a fire alarm system, it's actually stipulated as a performance requirement of the system. Generally, anything less than a score of 0.5 becomes increasingly difficult to comprehend. Other slightly simpler measures include C50 or C80, often collectively referred to as clarity, which assess the proportion of energy arriving within the first 50 or 80 milliseconds respectively, compared to later reflections. These measures give something of an indication of the direct-to-diffuse ratio, so how much of what the listener experiences is direct energy or supporting early reflections compared to later reverberant energy, which tends to reduce clarity. C50 is typically used in spaces primarily for speech, while C80, which allows for slightly more reverberance, is used in spaces for music. So these are just a few of the tools and metrics available to acousticians as we seek to design and quantify the performance of event spaces and sound systems. But how do we go about applying them? Well, the truth is that frustratingly, more often than not in the church, we don't. Many other types of buildings are governed either by strict acoustic standards or by industry-specific guidelines. So, for instance, residential properties are built to meet strict legal standards set under the building regulations, which include standards for their acoustics performance. For offices, we have British Council for Offices guidelines and other British standards, which are normally a minimum requirement. And for many developments, we also target higher levels of acoustic performance to attain credits under sustainable development schemes such as BREEAM and WELL. Schools and universities are constructed to meet acoustic standards specified in Building Bulletin 93, set by the Department for Education. Even sports facilities are often designed to achieve acoustic standards set by relative government bodies, so FIFA and UEFA for football stadiums, for instance. But in the church, we don't currently have any established guidance on acoustic standards. And this vacancy leaves a lot of room for deficiencies in the worship experience, either because acoustics and sound quality isn't properly considered within the context of the design of the building, or because it is considered but the wrong metrics are targeted. And I think this is a particular challenge for more modern expressions of the church, which are often not fully understood by secular consultants. So, for example, relatively long reverberation times of 2 to 3 seconds can be quite appropriate for churches which are still choral or organ-led in their music of worship, but it would be disastrous for contemporary congregations. Similarly, if the church is understood only as a place of spoken word and very short reverberation times are targeted, such as for a lecture hall, the musical aspect is neglected and communal worship feels very exposed and uncomfortable. Further research is needed to establish a consensus opinion on acceptable standards and to understand particularly the subtleties and differences between the various expressions of 21st century church, which obviously can be very diverse. Ultimately, I think it's up to us, represented here as the community of individuals within the church who are most passionate about sound and sound quality, to rectify this issue. And that's a challenge I want to leave you with. Thank you.